All right, can everybody hear me? Great. Okay, let's get started for today. Can somebody close the door in the back? So, welcome to lecture 5 on deep unsupervised learning. We will today cover implicit models, and a lot of it will be generative adversarial networks. Who has looked at Wilson's code for homework 1? Raise your hands. Okay, cool. Which one of you has given Wilson some feedback on his solution for homework 1? Nobody yet. Wow, solid solution, Wilson. That's great. I recommend actually, so about 10% of you looked at it. I recommend everybody look at it. I think the best way to learn something well is not just to try to do it, but also check how somebody else solved it. And that might be a good solution to check and see how it compares to how you did things. And it might actually help you a lot as you work in your homework too, because you might see tricks Wilson used that might be helpful for you as you solve your homework 2 and maybe also your research and so forth. Your homework 2, by the way, is already out and is due this coming Tuesday. So you have about a little less than a week left to finish that up. Any questions about logistics? So the slides that you'll find online are still a bit in draft stage for the full deck, but are more or less finished for today's lecture. We'll have 2 lectures to cover implicit models and GANs because it's just a very big topic, and we need 2 full lectures to get through that. In fact, you see here the menu we're going to go through. It's a lot to cover, all the way from motivation through the whole progression of GANs, different ways of looking at GANs, and then some other considerations we'll consider at the end. Today, we'll hopefully get till somewhere in the middle of the GAN progression. That's our target for today. And then we'll pick up the rest of the GAN progression next week and see the other views on GANs next week. All right, let's start with some motivation. Let's see. One thing you might have seen in terms of image generation is this tweet over here from Ian Goodfellow, who actually is the first author on the first GAN paper, so in some sense the inventor of GAN. And 2014 is when his paper came out, and it kind of looks like a face, but not necessarily high resolution, not particularly realistic. And then from there we see a progression in just 5 years to extremely realistic faces automatically generated by GANs. Then there's this thing over here, Big GAN. This is actually a video for Big GAN. Let me pull up the video. Here is the video. What we're watching here is we're watching interpolations between real images. So there's real images, and you can interpolate in latent space of GAN between those images, and then as you interpolate in latent space, generate the corresponding images that the generator would generate from that latent code. And the thing to look for here is that actually a very large fraction of the interpolations are very meaningful, meaning that somehow it's discovered a lot about the structure that is in our natural world around us and what makes for realistic images. Because many things in latent space will map to realistic images, and if you interpolate between 2 real images, you get something that's somewhat meaningful in between most of the time, not just an overlay of just averaging pixels. You can actually get different viewpoints on objects and so forth. So our goal is to better understand how to get these things to work and maybe also see what the future might be. Actually, very interesting that happened is in 2018, somebody took some code available on GitHub, trained a GAN on paintings, and then actually marketed really well and sold them at Christie's, which is, well, it's in London. It's where people buy art, and you bid, and actually somebody bid and paid over $400,000 for this AI-generated artwork with a signature, actually the equation that we'll spend a lot of our time today on, because that's the equation that effectively designed this painting. The funny thing, by the way, is also that the people who sold it did not invent GAN. They did not even write the code to run GAN. They did dig out the right training data, so you can train a GAN that generates interesting images that you can market and sell. So in terms of generative models and unsupervised learning, what we've seen so far is autoregressive models, made pixel CNN, RNN, gated pixel CNN, pixel snail. We've seen flow models, autoregressive flows first, then real MVP, glow, flow++. We've seen latent variable models. That was last week. The common aspect here is that all of these are likelihood-based models. The first two categories are exact likelihoods that we're optimizing against. And the third one, latent variable models, we had the variational lower bound and approximation of the likelihood that we would optimize for training. And so based on what we've seen so far, you might expect the next thing we're going to see is also going to optimize a likelihood, but we're actually not going to do that. Generative models, you might want to sample from them, evaluate the likelihood of a new sample or a given data point, train them, and find a good representation, some latent space. But what if all we care about is sampling? What might that open up maybe in terms of new opportunities? Well, if all you care about is sampling, how about this thing over here? What will this thing do? Any thoughts? Say it again? Right. This is just indexing into your training data and then displaying an image from your training data. So this is going to generate extremely realistic images. And so if all you care about is realistic images being displayed, you're good to go. But of course, we want more than that. This is not as interesting. What do we want from our sampler? We actually want somehow a generative model that can understand the underlying distribution of data points, and as a consequence, interpolate across the training samples in a meaningful way. Output samples similar, but not the same as training samples, so it generalizes. We want output samples that are representative of the underlying factors of variation in the training distribution. An example would be digit data set, and you might want to see another rendering of the same digit, but with different strokes, different thickness, thinner stroke, maybe shift a little bit to the left or the right. A variation that might not be exactly in the training data would be better than just putting back out training data examples. For faces, you might have seen faces in different poses, but for some faces, you might not have seen a certain pose. If it can generate that pose also, it means it understands something more about the underlying distribution, and that's what we're after. In implicit models, we're going to sample Z from a fixed noise source distribution. So Z will still come from uniform or Gaussian. We pass it through a neural network. Out comes X. This is just like what we saw in flow models and in latent variable models. What's going to be different here is that we're going to try to train this thing without explicit density estimation. We're just going to focus somehow on the quality of the samples generated and try to optimize it for quality of sample generation. Let's make this a little more explicit. What does it mean to be an implicit model? So let's say we're given some samples from a data distribution, P data. That's our training data. Then we have a sampler, Q phi, which takes our latent code and turns it into some output. Some deep neural network turns latent code into some output. Z comes from some simple distribution, uniform or Gaussian. X, Q phi of Z, will actually induce a density function. Just like we saw in flows, when you went from one space to another space, you induce a density function. But in implicit models, we did not have an explicit form for distribution over data or the distribution we use for our model. We can only draw samples. That's our assumption. So it becomes very different from what we've seen before. We're not going to have some kind of objective we can optimize. We just have some Z that's sampled and is supposed to be turned into a X space sample that is similar to the training data. And so what we want to do is make our distribution that we learn, the model distribution, as close as possible as the data distribution by learning some appropriate phi. But we're never going to have explicit access to P data or P model. All we're going to have is samples from our underlying data distribution and samples from our model. And somehow we want to compare those samples and train Q phi to make those samples close together. So it's quite different from maximum likelihood. So we now need a different way of measuring how far these two distributions are. With density models, we could just use the KL. Right? We had KL between the data and the model, and that was the same as maximum likelihood optimization, minimizing KL, maximizing the likelihood. And now we can't really do that because we will not have a P model in a parametric form. We will just have samples from the model. So we need to come up with a new distance measure. And within GANs, we'll see that there are actually quite a few different distance measures people have come up with. Variations on the same theme, but not always the exact same distance measure. And so some examples are maximum mean discrepancy, which we'll cover at the very end of next lecture. The Jensen-Shannon divergence, which we'll see approximately maybe gets somewhat optimized by GAN. The regular GAN, and then Earth mover's distance, which matches with what we'll later call Wasserstein GAN. So we don't know yet how to do this, but that's going to be the overarching picture. We somehow want to measure the proximity of two sets of samples and somehow backpropagate through that proximity measure to improve our sampler to get samples closer to the data samples. Yes?
Can you explain a bit more how to get PP model?
Yeah, very good question. Can we say a bit more about this thing over here? The big takeaway here is that we're not going to explicitly represent a probability distribution the way we have done so far. There's not going to be a P model of X that assigns a number to each possible data point X. Instead, implicitly, that's the implicit part, implicitly, we know that if we sample Z's, they will result in X's through the mapping that we saw in the previous slide. So this mapping will turn Z's into X's. So we know that implicitly, by choosing a mapping from Z to X, we are inducing a distribution, a model distribution. But we're not going to have a form for it in the sense that we're not going to have something that says, oh, the probability of this X is this much. Instead, all we're going to have is a lot of samples generated this way. And we're going to compare a lot of samples generated this way with our data. And we somehow want the two sets of samples to be close together. And when they're close together, that means your Q phi over here is doing the right thing. So we're going to optimize our Q phi to bring the sets of samples together, while keeping in mind, of course, we don't want this kind of sampler where you just draw data points. You want something that generalizes, that can interpolate, that draws variations on the original data. So it's not just about, oh, can we find something that's as close as possible, because then you just use your data. It's more subtle than that. You want the notion of generalization. So for now, it's a little subtle, and they'll become more clear soon. But I'd say the important takeaway is that this P model thing, we will not have any expressions of the type P model of xi and then some log in front of it and try to maximize it. It's not going to happen here. Okay, so let's take a look at the original GAN. Paper came out in 2014. Proposed a new framework for estimating generative models via an adversarial process. Okay? Simultaneously train two models, generative model G, captures distribution, and discriminative model D, that checks how different the distribution is that we're generating versus the data distribution. That's the high-level idea. Experiments demonstrate the potential of the framework through qualitative and quantitative evaluation of the generated samples. And since then, that potential has definitely been filled in by many follow-up papers. I think this paper might be cited 5,000 times by now or more. So what does the math look like? We're going to formulate it as follows. We're still going to try to find the generative process, G. And there's going to be a discriminator, D. And it's going to be a game between the two of them. So a minimax game, they're playing against each other. Let's first look at G. What is G doing? G appears only here. G is turning Z into X. So G of Z is X, lives in our image space or text space or speech, whatever you're trying to generate. So G of Z generates. Then what's the discriminator doing? The discriminator is trying to classify. The discriminator is trying to classify which x's are real versus generated. So here's our real, the data distribution. And we're going to try to maximize the log probability under the discriminator. The discriminator will have a 0, 1 output, well, a sigmoid output. Probability of being real. And so the discriminator will try to drive these to 1 as high as possible. So 1 is the highest probability you can assign to something being real. And then here, it's doing the exact opposite. It's saying the discriminator is going to try to drive this to 0, because those are fakes, which if the discriminator drives this to 0, because it's subtracted out, and there's a 1 minus, then actually the whole term will become as large as possible. So the discriminator is effectively trying to be as accurate as possible at assigning zeros to fakes and ones to reals. And it's doing that in a probabilistic way. Two of them play a game against each other. You can imagine what happens at convergence. If you're at Nash equilibrium of this game, meaning that nobody can improve anymore, well, the generator should generate things that look real, because then the discriminator cannot do anything about it. That's ideal. Discriminator at that point will output essentially 50-50. The way you optimize this, if you don't know what it is, you got to hedge your bets. You got to assign 50% probability to each side. That's at full convergence. Not saying it ever fully gets there, but that's how this game is set up. So it's really nice. You actually now don't need explicit probabilistic evaluation model for your P model. You can just try to solve this game, and the game is defined as try to generate things that are as realistic as possible. What might it look like? So you have, in some sense, two pipelines. You have X coming from your data, goes through D, and D tries to assign a probability of 1 of it being real. So that's a supervised learning problem right there. At the same time, there's another supervised learning problem here for D to assign essentially probabilities as close as possible to 0 of the artificially generated samples being real. And then in here, there is a generator. And so what effectively happens if you look at the math well, we can look at the algorithm. You're going to iterate. You're going to sample some Z's and generate, let's say, images to be concrete. Then you're going to take a mini batch from your data. These are the real images. Then you're going to look at this objective. You're going to optimize your discriminator to maximize its classification accuracy. This is just straight up supervised learning. You train a classifier, be maximally accurate on classifying real versus fake. You have some real data, some fake data. Just train it. Then the generator, going back to, if you look at the overall objective, which is this, generator only participates in this part, which is put back over here. And so the generator will try to minimize that term in the objective and does gradient steps on that part. And you just iterate over those two till hopefully you get to a good spot. So any questions about general setup? Okay, so then let's take a look at a demo. So what do we have here? We have GAN lab demo. We have a real distribution shown in green over here. Then as we start training, what's going to happen? As we start training, both discriminator and generator will be training. So let's hit play. It's not displaying it correctly, it seems. It's kind of unfortunate. Let me plug in my laptop. I think it should display better for this demo. So we have real data in green, fake data, samples generated in purple. This is before training, or let's reset. So it's completely before training. And then let's run play. And so what do we see happen here is, what we would hope to happen is that as the training progresses, the purple samples will match up more and more closely with the green ones. And then when a discriminator tries to distinguish which samples, which individual data points come from real versus fake, he'll have a harder and harder time figuring that out. And at some point, generator will, in some sense, win the game and be able to fool discriminator. And actually, in this case, it starts to work pretty well. The purple samples here are getting pretty close to the green ones, which means it's trying to capture the general gist of this distribution. So it's a mixture of Gaussians, and it's captured by this sampling process. Again, there's no explicit density model that we can evaluate. It's just we want the samples generated to be similar to the data distribution that we have. Then if we look at the thing on the right over here, what's going on is, effectively what's happening is for each sample that was generated, you have something saying if it had just been moved more in this direction or that direction, it would actually have been a better sample that would have done a better job at fooling discriminator, and you see the samples move around accordingly here. Let's do something a little harder. So this is actually working pretty well. I can see learning curves here. You now have two losses that you look at, by the way. There's a discriminator loss and a generator loss, and hopefully both of them converge at some point. It's a game, so it's a little more complicated to think about. It's not like you just see a curve that goes up, because there's two playing against each other. And so there's no such notion as you have in likelihood training. You just see it go up and asymptote to some correct number. Then let's make it harder. Let's 3 clusters. Actually, let's do this circular thing and see what happens. You see some oscillations on the losses here. That's pretty typical that sometimes the discriminator does a little better. Actually, often the discriminator tends to do a little better. Then the generator does a little better, and this can go back and forth. This, of course, depends also on the expressiveness of your discriminator network and your generator network. But this is the underlying dynamic that's happening. When we train for realistic things, so now we're going to be able to visualize it this way. It's not going to be in 2D. It's going to be high-dimensional image space. But something similar will be happening where somehow these samples and the real data are getting lined up, so they become indistinguishable for your discriminator network. This can also sometimes work really poorly, like you have a lot of oscillations happening here now. It's not really getting to a great convergence point yet. And so that's actually one of the big challenges with GAN training, that you don't get typically this clean monotonic improvements that you're used to with training supervised models or other unsupervised models. Okay, so let's go back to our math that's behind this. So here are some samples from 2014. The last column are real, and the other images are generated. Yes, question?
So we could use like our flow model using GANs. We don't have that many restrictions that allow for GANs to work so well.
Well, it's a good question. For GANs to work so well, I mean, in what sense do they work so well? So in some sense, they work very well in generating realistic images, right? That's in many ways their strength. And so part of that is that their objective is set up exactly for that, right? Because you have an objective that literally says, make your generated samples as indistinguishable as possible from data samples. And so GANs are very directly optimizing for that. And so part of what this hints at is that just optimizing for likelihood doesn't always 100% align with optimizing for looking like real images. And you see that, I mean, of course, some likelihood models are getting very close. And so that distinction has been actually reduced quite a bit. But in the early days, GANs would generate much more realistic images because they directly optimize for it. And so for a lot of people, the intuition is that likelihood models, when they're not getting very high scores, then it might not be perfectly aligned with realistic images. But once they get very high scores, do really well, they are also going to be starting to generate realistic images.
But you can add the GAN objective to any model that we've learned so far, right?
Can you add the GAN objective to any model? Yes, you can have multiple losses. Absolutely, if you want to.
Would that improve the image quality, the generated to sample the image quality of all our models?
If you added the GAN objective, it would likely improve the sample quality because it's directly optimizing for that.
So why is this proposed as like an alternative method rather than just like a wrapper around our original?
That's a good question. I mean, I think in some sense what you're getting at is that throwing the kitchen sink at something is a great idea very often because you throw the entire kitchen sink at it, you might get better performance than doing something more clean. And I think educationally, it's more interesting to see the individual parts, see what their strengths and weaknesses are, rather than just saying, let's take everything everybody has ever invented, put it in one model, and put it in front of you. So that's the reason. And same with writing papers. You don't want to write a paper where you bring 1,000 things in, and then nobody can understand where it comes from. It's really about generating insights and understanding. But at some point, you're just an engineer. And when you're an engineer, not a researcher, you might just want to say, I want to bring everything to bear. I don't care. I'm not trying to generate insight. I'm not trying to make anybody understand what's going on here. I'm just going to bring everything to bear and see what comes out of it. And that's a different mindset. But it's a good question. You could combine everything. And for your project, you could maybe combine all 4 classes of models we've seen so far in some way. Question? Yes?
Is there something preventing the generator from just memorizing some key set of examples?
That can be a problem. The generator might memorize some examples. In principle, the discriminator should understand that. So in principle, if the generator generates, let's say, 5 of your data samples every time, the discriminator should learn that whenever it sees those 5 out of maybe 1,000 training data, those 5 are always by the generator. And that also, not always, but most of the time. And so if the discriminator is faced with those, it'll say, oh, likely generated. Even though sometimes it's real data, most of the time it'll have been generated. And so that's the counter force to that. It's not perfect. I mean, you'll see that these kind of similar things do happen if you're not careful. But in principle, this objective gets around that if it's optimized completely by being able to recognize that.
But the limiting case of that, if you were able to somehow memorize your training data perfectly, would that be a breakdown?
If you can memorize the training data perfectly, that would be a breakdown. And so you don't want, essentially, you don't want to set up a generator network that would memorize your training data. Do you want to set up your generator network to take in, let's say, Z samples from a Gaussian distribution and turn that into some continuum of images, not a discrete set of images? But yeah, in principle, you can set up a network that turns your Z into one of your training data images. You don't want an architecture that could do that. So how to evaluate this? Evaluation for GANs turns out to still be a bit of an open problem because you cannot just report the kind of numbers we've been reporting so far. One thing you can do is say, well, if I can generate samples, I can think of it effectively as a mixture of Gaussians in some sense, where around every sample I put a Gaussian blob. This in turn yields a density model, and now I can evaluate for some test data, what is the likelihood of some test data under this mixture of Gaussian kernel density estimator model, and report those numbers. Some playing you have to do with the bandwidth. Even for 1D examples, you could see for different bandwidths of your kernel, you'll have different smoothness of curves. So the reference is shown in gray. You want to be as close as possible to the gray. The black little stripes at the bottom are the samples. And then depending on the bandwidth, for a very narrow bandwidth, you get the reddish curve, which is very high frequency. For green, you get something intermediate. And then for blue, you get a pretty smooth curve. So that's a wider bandwidth. And we'll have a higher likelihood score on your test data because it's much closer to the actual distribution of your test data you ultimately will care about. And people who did this in the early papers, people would compare these scores. The big issue with this, of course, is that it only works for low-dimensional data, because for high-dimensional data, putting these Gaussian blobs around generated samples, it'll still not really fill the space. Or if you wanted to fill the space, you got to make very high standard deviation Gaussians. It's just not a great metric. But in principle, you can use it and report on it. Here's another reason why it might not be the best metric. On the horizontal axis here is number of samples on logarithmic scale. And this is, I believe, for 6 by 6 patches. So not even that high dimensional images. And it's all 6 by 6 patches. And you then have a generator, and you generate samples from it, and you see what the log likelihood is of your test data as a function of how many samples you put into your sampler to build your kernel density estimator. And you see it's not getting anywhere near where you want to be, and it's not going to get there anytime soon. So that's for 6 by 6, 36-dimensional space. So you can imagine for megapixel images, it's going to be even worse. Turns out in the Theis paper, they actually play a little trick. You can go check in the paper that if you play some weird tricks, you can actually get a higher score than you're supposed to be able to get with the actual underlying density. So you can go check that out. What people have mostly switched to is something else, something called Inception Score, and then another score we'll see soon. So how do we sidestep this high-dimensional density estimation? Well, good generators should generate samples that are semantically diverse. So semantics predictor could be a trained inception network, V3, so you train a network on ImageNet, and you fix that. And then y given x, where y is one of the 1,000 ImageNet classes of what this thing outputs. So what would happen then is each image x should have a distinctly recognizable object. So if you train on ImageNet, and now you generate new images, each image you generate should somehow belong to a class. That's the intuition behind this, and that's what it's going to score. And you should also generate all classes. It shouldn't be that you always generate the horses, because then you're not generating a very diverse sample set. So high-level intuition, a classifier should have high confidence on the samples generated. That means they look a lot like the data distribution, which the classifier also has high confidence on the samples. And the samples should belong to many different classes. So the Inception Score does exactly that. You have the Inception model pre-trained, nothing to do with GAN, just a classifier model. You look at the marginal label distribution. So you generate data. You look at how often you get each label, and that gives you a 1,000-dimensional histogram in some sense. And then the Inception Score looks at the KL divergence between the conditional of y given x and the marginal. So the marginal ideally will be uniform, and the conditional ideally will be highly peaked around the 1 out of 1,000 classes that you just generated, and there'll be a very large KL divergence. So this is a case where your KL divergence, actually, if it's high, it's a good thing. You're hoping for a high KL divergence here. Generally speaking, I talked about the extreme case where it's generating exactly what you want. Generally speaking, the less uniform y is, the more difficult to have a large KL divergence here. And the less well you classify, also the harder it is. Because if you have a very poor class, let's say your data you generate is not clear what class it belongs to. Now you have a close to uniform distribution, maybe what it might be, and then these two become close together again. And so this is really optimized for the two things we care about: clear images in terms of class and making sure all classes are covered about equally. Another way to think of it is that it's measuring the entropy in the class labels you get out of this process and subtracts out the entropy of y given x. You want very low entropy of y given x, which means you generate a very clearly classifiable image, and then this thing will be very low. So here are some images generated with different methods. So this is the real data. This is the GAN proposed, and this is from the improved training of GAN papers, so the images from that, some previous models. And what we're looking at here is that the more realistic the images become, the higher the Inception Score. And so we see a good correlation between Inception Score and realism of images. Now, does it capture everything, this Inception Score thing? Well, there are some corner cases it really doesn't capture. So close to your corner case, imagine you only generate, from the 1,000 classes, you generate one image of each class, and that's all you do. Then, there are clear images from each respective class, but you have no other variation in your data you generate from your GAN. It will have a really good Inception Score. In fact, perfect score. Uniform over classes and clear classification for each image generated. So there's another score that's become popular, Fréchet inception distance, which looks at, as you generate an image, process it through a convnet that might again be pre-trained with a classification procedure. Then somewhere along the way, take a hidden layer, look at that vector, and think of it as the representation of that image. And now look at, on your training data and on your generated data, what is the distance between the mean of that feature vector that you just generated? And also compare the covariance matrices. So you look at covariance over generated data, you look at covariance over training data, and you compare the two covariance matrices here to see how close they are. And if they're close and the means are close, then there's a good sign that you're generating data that is a lot like your underlying distribution. Obviously, these are not perfect metrics. As I said on the first slide about metrics for GANs, it's still an open problem to have really good metrics. If you had a really, really good metric, you could probably use it as an optimization criterion, optimize against it. The two we just described are not good ones to optimize against. If you optimize directly against them, you'll find solutions that are not exactly what you want. But assuming you're not optimizing directly on them, they can be a nice independent measure of the amount of variation and crispness of the pictures that you're generating. And so in the Fréchet inception distance paper, they compare it with the Inception Score. And we see here that as you disturb more, the inception distance goes up, which is a good thing because it means you're not doing as well. So you have a worse score. Up is worse here. Whereas the original inception stays constant, doesn't really change. And so you definitely say this is a worse generator than that one. And Fréchet captures it, but original inception score does not. Similarly here for making it more blurry. Very clean curve for Fréchet, not so clean for the original inception score. And there's a few more comparisons here with, again, noise introduced. Fréchet captures that this is not as realistic, gives a worse score, whereas Inception does not. So, key pieces of GAN are fast sampling. You just go sample a Z from Gaussian or uniform and then turn it through a neural net into a sample. We're not doing inference, so we're not going the other way, not anything we've described so far. Next week, we will look at how we might be able to go the other way, but for now, haven't looked at that. And then the notion of optimizing directly what you care about, which is perceptual samples. That's what's in the optimization objective, which is a minimax game. So now we've covered the basic algorithm. Let's look at some theory behind it. Again, theory of GANs is not perfectly understood. These are just some hints at how you might be able to better understand what is behind GANs. So one question we could ask is, what is the optimal discriminator given a generated and a true distribution? Any thoughts? Let's think about this in a very simple case, right? A very simple case, you might have two distributions. Maybe a Gaussian, another Gaussian. And you could actually ask the question, right, what is the best way to distinguish where my data come from, Gaussian 1 or Gaussian 2? Well, if they have equal standard deviation, then you'll say, okay, on one side here it's one, on the other side it's the other. That's your best guess. But you can actually even compute a posterior. You can be Bayesian about this. For any point, let's say a point over here, you could look at the ratio between these two, and from that understand the ratio of probabilities that it came from one or the other. So in principle, that's possible. If we have two processes, we should be able to infer the probability, the exact probability it came from one or the other, assuming we had access to the models. For this theoretical analysis, we'll assume we can somehow write out the model and do some analysis with it. Okay, so let's take a look at what we can do here. Stepping through the math. This is our objective that we look at for our discriminator. All right, we're trying to find out to maximize the likelihood of this thing for our discriminator, which is here and here. Let's write this out explicitly as expectations as integrals, here with respect to the data, here with respect to our z's. Now, z, our distribution over z results in a distribution, a generated distribution for x, which will change a variable here, generator for x. Once we have both integrated with respect to x, we bring that out, and we have this quantity over here. And so we now have an optimization problem where we have p data x, p gx, and then d appears here and here. We can now take the derivative with respect to d of x and find for a given x what's the optimal d of x here, what's the posterior probability. So let's do that. That's really a problem of this format over here. And what we find is that this is the solution. And so our optimal discriminator will be this. The probability I assign for this coming from the real data is probability that was generated from the data divided by probability generated from the data plus probability generated from the generator. So we have a form here. And what we have here, maybe we have a data distribution, a generator distribution, and we can then know exactly what our optimal discriminator would look like. So now we can do a bit of extra math. What we can then do is we can say we have an expression for our optimal discriminator. If we fully optimize our discriminator, we can fill that expression into our original objective and see what, if the inner loop is fully solved by discriminator, what it looks like. So we're going to fill into discriminator here, optimal discriminator. We fill in that posterior probability. If you look at this expression over here, it's some kind of expectation with respect to data, then some log ratio, expectation with respect to the generator, some log ratio. That should remind you of KL divergences. You have distribution of KL where the data comes first, some KL where the generator comes first. But then, and indeed, we see data and then data at the top. That's exactly the KL we're seeing here. Same thing on the other side. But then on the bottom, we see a sum of two distributions. So it's really an averaging distribution sitting here, same over here. So what we see is that actually, if we look at it carefully, assuming the discriminator fully optimizes, and that's an assuming the discriminator does that. I mean, it's not easy necessarily to do that, and we'll see we might not want to do that. But assuming the discriminator fully optimizes, what happens is that the generator is trying to optimize a type of KL divergence between distributions. It's called the Jensen-Shannon divergence, which is a KL between the data and the average between data and generator, and between the generator and the average between data and generator. So actually, we're still optimizing something like a KL, but a different one than we looked at before. Remember, if we did maximum likelihood, it would have just been KL, P data, PG. This is maximum likelihood. So this is a little different. Let's take a look at what this comes out as when we optimize for, we have some data in 2D. It's our actual data. If we do KL, so maximum likelihood, we get this thing over here. What is it doing? It's ensuring that there is a lot of probability over here where most of the probability mass is, but also spreads out over the entire space, because if you don't cover some data point, it's going to give you a negative infinity score, and that's bad, so you got to cover everything. This one we'll skip for now. It'll come back next week. Then the Jensen-Shannon divergence, we see actually sit over here. It decides to assign pretty much all its probability mass on the biggest mode. And that happens to be the optimal thing to do here. Why is that happening? Well, it has these two terms. And one of the terms is a lot like the maximum likelihood term, but the other term is actually a reverse KL. It's where the data and the generator are swapped. When you swap, let's say you have a real distribution that has two modes. Maximum likelihood will hopefully find this thing. That's the best scoring distribution you can have. But the reverse KL will actually find this thing over here. It has a higher score for focusing all on one mode rather than spreading it out equally over both modes. Now, the Jensen-Shannon divergence is not exactly reverse KL. It's something in between reverse KL and forward KL. And so it's not zoning in on the mode maybe as much as a reverse KL would, but it'll still have that property of liking to zone in on it. Here's an example Alex made to show difference between the three. So our data distribution here, P of x, is shown in blue. So it's bimodal with a large peak on the left and then a smaller peak on the right. The maximum likelihood thing over here, this is the normal KL, will find something that kind of spreads out its probability mass in a decent way. Reverse KL will put it all over here. Not all, of course, is still fitting a Gaussian, but it's concentrating as much as possible right over there. That gives you the better score. Then the Jensen-Shannon divergence does something in between, puts most of the mass on that main peak, but still puts a bunch of mass out there onto the other peak, more so than the reverse KL would do. And so you might have heard of things like mode collapse in GANs and things like, what does it mean to have modes that in some sense disappear? What's happening is that, well, let's go back to this picture for a moment. The JSD distance metric, will prefer zoning in on specific modes, which means that this mode, if you look at your generator, will pretty much not appear. And it'll actually be optimal. It's what it's optimizing for. Whereas if you had a maximum likelihood model, it'll really have to cover everything. And we talked about this with the VQVAE, where we saw samples from VQVAE that had a wider coverage than what we saw in the big GAN samples at the time. So for compression, you would actually want to ensure all points in the data distribution are assigned some probability mass. Otherwise, you cannot compress the ones that are out of distribution very well. For generating good samples, blurring across modes actually spoils the quality of your samples, because as you start blurring across, leaking between two modes, the things in between are not going to look very good. And by covering the space in between, you get not so good looking samples. Picking one mode without assigning probability mass on points outside can just give better looking samples. Quick caveat here. The reason we had to make a trade-off is because what we're fitting is a unimodal Gaussian to a bimodal Gaussian distribution. If we were fitting a bimodal Gaussian to a bimodal Gaussian distribution, we could fit things more closely and we would not have to make this trade-off. And so as you have more expressive models, you are likely to suffer from this less because your model is able to capture many modes while not needing to put probability mass in between where you would get unrealistic samples. But in practice, I mean, depending on the complexity of your data, high dimensionality of your data, and the neural nets you're training, you'll often still see behaviors like this where your target might be, in this case, 8 modes, but then during training, you just jump around from mode to mode to mode, because what's happening is you're here. Now, the discriminator is like, well, when you generate something there, it could be real, but it's only 1/8 of the samples that are real land over there. But all the fakes land over there. So the discriminator is going to say, well, if I see this, I'm going to say fake. And then you get a bad score here, and you got to run somewhere else where the discriminator hasn't caught up with you yet. You're in another spot, and at some point the discriminator catches up and says, well, if you generate here, that's no good. I know that is generated because only 1/8 of the real samples will come in that spot. And you get in these cycles where generator hops around from mode to mode to mode. Discriminator catches up, and generator hops around again. So that's one of the challenges with GANs, the mode collapse and making sure you can cover modes. Another thing that's actually quite challenging is, well, let's look at this objective over here. This is our discriminator objective on the inside. This is just a classifier. Is it feasible to run the inner optimization to completion? We run it all the way until we get that base optimal classifier. Well, is it? Well, if you train your inner loop for long enough, you can actually get there with an expressive enough network. You will get there and get the base optimal classifier. Would it create problems if we're able to do so? It actually will create problems. The reason it will create problems is that once the discriminator becomes very confident, there will be no gradient left. So the discriminator, here we have, in this plot we have y equals sigma of x. Then this is our objective, log 1 minus sigma of x. Inside of here, x equals g of z, right? Well, it's a little more complicated. In some sense, the x here is most of the discriminator of g of z, and then sigma comes at the very end of the discriminator. And so what lives inside here is the generator objective. When the discriminator is extremely confident and is 100% sure what you generated is fake, it will not, and any small change to your generation process, the discriminator remains 100% confident it's fake. That means there's no gradient signal, and you cannot improve your generator. If you look at it specifically here, discriminator, once it's becoming very confident, which means for discriminator to be confident means that when we are getting a fake image, that's what we worry about. There's a fake image being generated. Discriminator is very confident it's fake. So fake image, discriminator is confident, means it generates something close to a 0. You're on the 0 side, or in the x space, x would be going to negative infinity. So the sigmoid turns that into a 0 probability of being real. At that point, you're all the way out here where this objective is extremely flat. And now if you look at the derivative, which is shown in this plot over here, is 0. So you get no signal from your discriminator about how to improve your generator to get better samples in the future. This is called discriminator saturation. It's this notion where if your discriminator trains for a really long time, or not even that long time, it's just expressive enough to be really good quickly, what will happen is the gradient for the generator will effectively disappear. And so what you really can do instead, or should do instead, is an alternating optimization. Don't optimize your discriminator all the way till the end, till it's near perfect in your current generator, because then you will get no signal anymore. That's one solution. Another thing you can do that's often done is reformulate your objective to be non-saturating. It's a little bit of math here, but let's actually look at the plots. Here is our y log of 1 minus sigma x. And instead, we can maybe look at y equals minus log of sigma x. This is a slight tweak to the objective. It's looking at the other side in some sense. You have two terms in your objective, log of sigma x and then log of 1 minus sigma x. And the log of sigma x is living in the front of the two terms. The other one is log of 1 minus sigma x. By flipping this to minus log of sigma x, you are living in a different regime. So you're living on, you know what the problem is? The problem is always when discriminator confident leads to this x going to negative infinity. So that led to the problem that this is flat here, and so your derivative is 0. If instead you say, I'm going to optimize the negative log probability of just sigma x, you get an objective that looks like this, which has a slope here and becomes flat on the other side. And so, but this is the side we care about, so where the discriminator is very confident that it's a fake, and we see we get a derivative of negative 1, which is not 0, and we get all the signal to propagate. You might say, well, isn't it bad that we have a derivative of 0 now on the other side? Because we're choosing with this process. Either we have a no signal when the discriminator is very confident it's fake, or no signal when the discriminator is very confident about it being real. In practice, once the discriminator is very confident your generated samples are real, you actually don't have as much of a problem. You're now generating real samples, so you're kind of good to go for your generator. The problem is when initially you generate bad stuff and you get no signal to improve upon it. And so by changing the objective from the original log 1 minus sigma x into minus log of sigma x, you get that effect. And here it's done for the overall objective. Originally we had this, which is a minimax game, and we're replacing the second term here only for the generator with instead this thing over here. And now we keep getting signal no matter how confident our discriminator is, it's not capping off the signal anywhere. Any questions about this? Yes? Say it again?
Before you have insurance inclusion so that you calculate the equivalent length in the 15% perfect point, but if you change one of the formulation, does that change the...
Oh, good question. So at the top here, we have a minimax game that has a well-defined, we might not be able to find it, but has a well-defined minimax equilibrium, a Nash equilibrium. Once we switch to running this optimization here, our discriminator has a different objective that it's working on than the generator. So this will not be a clean min-max two-player game anymore. It's still a two-player game in some sense, but it's not a min-max game the way it used to be, kind of zero-sum. Instead, the utility function for the generator is somewhat different and not going exactly against the objective function of the discriminator. So it has different properties when you run this. You can't claim the same things about Nash equilibrium that you could claim for zero-sum games, because non-zero-sum games have not the same kind of properties. In practice, though, typically works better to do this because you don't lose the signal. Because typically the difficulty in training GANs is that initially the generator is not good, and then the discriminator is so powerful, and now you get no signal, and you can't train. Yes?
How do you decide how long you stay in a particular phase? And also, have there been any guys looked at like decreasing or just adjusting those intervals over the training cycles?
Yeah, that's a really good question. I mean, you're referring to the algorithm here, right? Where is it? Over here, original algorithm, the paper. I mean, they have like for k steps, do this, which is discriminator updates. They say we used k equal 1, so they don't do too many discriminator updates, just exactly 1. But in principle, you can vary that. Same with the generator. You can, in principle, vary how many steps you do on the generator. So yeah, there's a lot of hyperparameter choices. And what you'll see as Aravind steps through the whole progression of GANs is that there's a lot of hyperparameter choices that can make a difference. There's a lot of architecture choices that will make this much better behaved. And so bringing all these things together is what has resulted in the results we see today. Just naively running it as formulated in 2014 is actually not going to give you that great results. You need to be really careful about all the details to make this work. Yes?
I'm wondering if anyone has experimented with sort of more liberal loss criteria than just sort of the Bayes optimal loss. So something like false discovery rate instead of just pure accuracy or some class.
Sure. Let's maybe hold that question for the end of next lecture because we're going to see a lot of variation. You're essentially asking about variations, and the remainder of this lecture and next lecture is pretty much all variations. So let's see what the questions are at the end of that. Yes?
For combating non-saturation, couldn't you have another term you multiply your loss by depending upon how confident your generator is and basically boost it up artificially by a factor of 10 or 100?
Yeah, so the question is, can you play some hacks where maybe, even though the derivative is near 0, maybe you can boost it up and still recover some derivative? I suspect you can make that work. It might not be super convenient, but there might be a way to make that work. But in fact, a lot of the variations we'll see will also actually have a specific formulation to avoid that saturation. So sometimes people build it into the objective in the work that's happening now rather than trying to, after the fact, correct for it. Aravind, want to switch over to you?
Cool. So you've seen the basics, like the foundational math that lets you understand GANs. But as Pieter pointed out, if you just go to the old Goodfellow Theano code and just try to run it now, you're not going to get the kind of results that you're familiar with the latest GANs. So let's actually look at what has helped make this progress. And it'll be a lot of emphasis on architectural and engineering details. But at the same time, we'll also give you some foundational ideas that have also enabled these kind of things to happen. So the first step is we look at this architecture called DCGAN, or Deep Convolutional Generative Adversarial Networks. This was a paper by Alec Radford and collaborators way back in 2015. Basically, their motivation was that they wanted to do representation learning. It was not particularly to generate images. If you look at the abstract, they basically show that like unsupervised learning has not, with convolutional neural nets, has not received much attention, which is really true at that time because people weren't really pushing on unsupervised learning because CNNs were just working and there was a lot of things to do in supervised learning. So they basically are proposing DCGANs as a way to learn good features, do good unsupervised learning, and use these representations from the generator and the discriminator and show that they can actually be pretty useful and capture useful aspects of the image. So a big part of the DCGAN architecture is the adoption of convolutions everywhere. So it's not that the original GAN was not deep, or it's not that the original GAN wasn't using convolutional layers. It's more that it was not deep enough and it didn't use sufficient convolution layers. So, and that's really how deep learning has progressed over time. You just add more layers and you just use better layers and you get better results. So if you start, so this is a 100-dimensional Gaussian that you sample. This is a noise you sample. and you project it up with a dense layer, and you get 16,000. Let's say you get 16,384 units, and you just do a reshape and make it spatial now. So that you reshape it to 4 by 4 by 1024, and then after that you don't need to use any dense layer. It's just going to be a bunch of deconvolutional layers. For those of you who are not familiar with this word, it's just the transpose con, which is basically what happens when you do a backward pass of a normal con, which is the transpose of that. And so that lets, if you use it with a stride greater than 1, it lets you upsample, because the backward of that would be downsample. So from a 4 by 4 by 1024, every layer, what you're doing is you want to spatially upsample, and you want to do channel downsampling. So this is really the inverse of what you do in a supervised model, where in a supervised model you start off with a big image, but very few channels because you have RGB channels. And then over layer by layer, you're basically reducing the spatial dimension, but you're increasing the channel dimension. So the inverse of that happens in a generative model, because you are starting with just noise, and you're trying to get all the way up to the actual image. So you can see that you go from 8 by 8, 16 by 16, 32 by 32 to 64 by 64. At that time, 64 by 64, generating a 64 by 64 image was considered a big deal. So you could imagine, like, I mean, it's not that they didn't try to do bigger images. And you can also see that the channel dimension is being reduced by a factor of 2 until the final layer, which gets 3 channels. The final thing I want to tell you is that images are pixels, right? Like, their RGB values are pixels. So just 64 by 64 by 3, just that tensor is not going to be an actual image unless you force it to be. So what people usually do is they normalize your input pixels to lie in the range -1 to 1. That's just obtained by you just take your image and you just divide by 127.5, and you just subtract 1, right? So basically your pixels are normalized to lie between -1 to 1. So when you try to generate it, you apply a tanh nonlinearity at the end, and that lets your model output. That lets your generator output values that are lying between -1 to 1. This is very crucial because at sampling time, you should be able to go back to RGB values. So there are lots of more details. Just that architecture is this fundamental part, but not the only part. So usually, a discriminator is a normal classifier. So or you can interpret it as a classifier. So for that architecture, you're just going to use a regular convolutional model that you use in supervised learning. So in such models, typically in those days, people used to use max pooling and probably mean pooling in the middle. So those are not particularly good for generative models. So these are removed from the DCGAN's discriminator. And whenever you do the upsampling in your generator, you're using transpose convolutions. And when you do downsampling in your discriminator, because your discriminator is going to take a 64 by 64 by 3 input and try to go all the way up to a single value, which says like real or fake, right? So you'll be downsampling in your discriminator exactly like mirroring the generator, like whatever resolution you got at the end, it'll be in the beginning in the discriminator. So there you're going to use strided convolutions to do the downsampling, and you use average pooling only at the end before predicting this value. Just like how in a classifier you just use mean pooling at the end. You never use it in between. And for the nonlinearities in your architecture, it was very crucial for them to use a leaky ReLU nonlinearity in the discriminator with a slope of 0.2. This is a leaky ReLU looks something like this, where the negative x part is not 0, but it also has a slope, but it could be a different slope from the positive x. and usually it's a smaller slope. So this is important because your gradients could become really sparse while training something very complex like a GAN. So they wanted to use something that doesn't zero out very quickly, and so they used leaky ReLU in the discriminator. And then finally, so this is actually a difference from the original GAN models, because the original GAN models used the max out nonlinearity. And like I said, there is a tangent for the generator, and the discriminator is a binary classifier, so you use a sigmoid output at the end. So those are the output nonlinearities. And most importantly, in DCGAN, batch normalization is used for preventing mode collapse. This is not a principal solution by any means. It's an architectural solution. But it was crucial not to apply it at the output of the generator or the input of the discriminator. And this is not a random choice. It's because batch norms are usually applied before a ReLU or a leaky ReLU nonlinearity. It's always like you follow up a batch norm with a ReLU. And at the output of the generator, you have a tangential nonlinearity, and the input of the discriminator, there's no, like, your generator outputs are actually like in a normalized range already. So, and your input from the data distribution will also be normalized already, to lie between -1 to 1. So there's no need to apply a nonlinearity there. So it's a pretty principled choice not to use the batch norm at these two locations. Finally, in terms of optimization details, they use an atom step size of 2e-4, and they don't use a very aggressive momentum. So that's probably telling you that how like optimization is a big issue, and like, you know, having too much momentum or no momentum is going to like make your models not train that well. So they pick a very reasonable momentum value, and they train with a reasonably big batch size. 128 was probably considered big at that time. And all these are very crucial details to get these results. So DCGAN can be summarized as basically taking the promise of a new technique like GAN, which was not proven yet, and figuring out lots of details and getting results for the first time, which were amazing. And we'll see why we'll see some of the results. So one final point I want to make is how you apply the batch norm to the discriminator. So if your discriminator looks at both X coming from your generator distribution and your X coming from your data distribution. And if you construct a mini batch that has some real and some generated, and you pass into your discriminator, your batch statistics are going to be average across all of them. And this is generally not a great idea. But it is both intuitive and counterintuitive. You could think about it in both ways. In terms of helping, you could think that it could try the batch normalization is averaging to what's relevant at the moment for the generator. So you could think about it in a helpful way. But in a non-helpful way, what you could see is like the statistics are getting corrupted with some noise, and like so it's not really learning to figure out the actual statistics that matter, which is your real distribution. And so it's a pretty messy choice. But turns out that when you actually implement models, when you write code, when you do a particular forward pass and you're just writing min for last discriminator and then you have another step, which is if you're using the non-saturated version, you're maximizing the discriminator loss with respect to the generator parameters. You just do separate forward passes, and this is implicitly ensured. But this was sort of like, they thought it was a bug, but it's actually not a bug. It was pretty useful. So that's another subtle point about batch norm and the discriminator. So in terms of results, DCGAN was really, really good for generating images of bedrooms. That's not the goal, of course, but it was the bedrooms data set is this Elson data set. A particular subset of that is bedrooms. There are lots of other subsets, but this is a pretty constrained data set. It doesn't have a lot of variety, but it still has sufficient diversity enough for you to like train generative models and see what's going on. And the bedrooms look pretty realistic and pretty diverse, so that shows that DCGAN could work and produce realistic images for the first time for a GAN model. And they also scraped data sets of celebrity faces from the internet, and they trained it, and you could see that it's actually generating pretty good, pretty promising faces for any generative model at the time. And the nice thing is you could also interpolate in the latent space. So you could take a particular noise vector Z1 and another vector Z2 and take a lot of points in between. And as you keep moving along the Z, you could keep getting different X's. And you could see that it's basically changing the viewpoint of a bedroom, or like changing, it's sort of like a camera that's moving around basically. So you could think of like one of the latent variables as basically the position of a camera that's capturing the scene. So it's implicitly understanding the formation of an image, the process of forming an image, even without any geometric constraints baked into the model. One subtle point about this is it depends on how you take the Z's in between. You could imagine taking a high-dimensional Z1 and a Z2, and you could take all the points in the straight line, or you could think of all these coming from a spherical Gaussian, and you take one particular point and another particular point. You just take the circle that is in the sphere, and it turns out that you can produce better samples if you sample from the circle instead of taking just a straight line. This is not used in the DCGAN model, but in the later demos of GAN sampling or interpolations, the people prefer to use the spherical sampling. And for the first time, actually, any generative model produced some reasonably good-looking samples on a big enough data set like ImageNet, which has 1.28 million images, but they only trained it on the 32 by 32 downsample version. Prior to this paper, there was another paper, Pixel RNN, which also is shown to work on 32 by 32 ImageNet, but the samples from DCGAN are like more realistic looking than the Pixel RNN samples. So a most interesting aspect in the DCGAN results was that you could do vector arithmetic. So a lot of you who are familiar with the word-to-vec models in language, you would know that people used to do these very interesting aspects, like taking two different words, taking a third word, and like subtracting the embeddings and seeing what it gives, like what is the closest neighboring word in your data set, and like figuring out all these nice linguistic understanding. And turns out the same thing can be done for images with the DCGAN model, where you take latent, you get a smiling woman, and then you get you subtract the embedding for a neutral woman, and then you add the embedding for a neutral man, and so that way the neutral gets subtracted out, you're adding and subtracting it, and you're ending up, and you're also subtracting women, so you're ending up with a man because you added a man. So these are like nice latent properties. It's very clear that the Z vector is able to capture, like the correlations between the Z and the pixels it generates is able to capture these high-level semantics without any label data, right? So that was very interesting because that means that these models are actually capturing some, doing actual unsupervised learning. And there are more results similarly, like a man with glasses. You subtract man without glasses, and you add woman without glasses. You get a woman with glasses. And these are various different samplings, right? You can sample with adding different noise, and then you can see different samples. Whereas if you do it in the pixel space, if you just take the image, you just subtract the pixels and add the pixels to the other image, the results aren't that good. They look pretty noisy, right? So it's very clear that the latent space is so crucial. Finally, like I said, the interpolations really worked well in spite of just doing it in a straight line. And you could see that it's understanding the concepts of like poses, right? Like if you could imagine this, if you think about the G that transforms Z to X, think about this G as some like the equivalent of a graphics engine that's been written with neural networks, right? So you're feeding in some input parameters, and it's rendering the actual image. And as you keep changing some of the values in your noise, it's behaving as if it's changing the pose in the renderer, right? And then it's slowly changing the texture and going to the target face. So that's really cool. And that's really what you want a generative model to do. In terms of the representation learning results, which I believe was the main focus of the authors, they took the discriminator that was trained in the DCGAN process, and they actually try to put a classifier on top. And even though the DCGAN model was trained on ImageNet, unlabeled data, they took that DCGAN model and put a classifier on top and tried to train it on CFAR, where the convolutional layers have been trained from the GAN training process. And they showed that it could do better than a supervised model, competitive supervised models at the time, and it could get 82.8% top one accuracy on CFAR, CFAR 10. So that was very encouraging. It's not as good as so this was a self-supervised method, exemplar-based method, and that was doing better than their model. And there are other models like the work from Adam Coates from Stanford. He'd done a lot of k-means-based methods for CFAR, but it was pretty competitive with those methods. So, yeah, it was just, so Peter's question was, would it just fine-tune the discriminator? The answer is yes. You just take the model, you put a classifier on top, and you just fine-tune it. They also tried, I think they also tried just freezing the features and training an SVM on top. So both of them work pretty well. Any questions so far? All right. So DCGAN produced incredible samples for any generative model for the first time. Even though pixel RNN existed at that time, DCGAN samples were more diverse, bigger images, bigger resolution, way more realistic. And so this was exciting for any generative model. And this was exciting for GANs, because GANs was started off like an academic paper with a weird idea, which is very, very, very fancy, but not working. But then, with a lot of hacks and architecture details, it started working, and it was perceptually good. The interpolations, I guess, interpolations were great, and then the representation learning aspect was also very exciting. The problems to address was that the training was really unstable. If you look at all these hacks, all these hacks exist because they were not able to get it work without those hacks. So there's a lot of brittle architecture and hyperparameter choices. And one point that that is not really a negative, but I would like to make is, because you use batch num in the discriminator, when you sample and in the generator, you need to sample at test time in a batch mode, right? So what this means is, in supervised learning, if you use batch num, you use a running average of your batch statistics at every layer, and then you use just those statistics at test time. But in generative models, what the DCGAN authors did is they didn't use the training time statistics. They just used they just sampled again on batch mode at test time. So they would sample a batch of Z's, and then they would just pass it forward to the generator and get the images. And the batch num is just going to happen to whatever samples you feed in. So the samples that you get are be quite correlated across your batch, and also it's going to be very much dependent on what your batch size is, because you usually want to use a bigger batch size for batch num to work really well. And it's also very likely to be very different for different samplings. So that's not technically it's fine to do like this, but in a principle sense, you would want the generative model to be a sampler no matter how many samples you want to see. So that's like a sort of a negative architecturally. So given all these negatives, the next paper that was pretty significant in GANs was to address some of these negatives, try to propose fixes. So just in the DCGAN sense, it was also a bunch of another set of some principle and heuristic hacks to make GAN training even better. And that is this paper called Improved Techniques for Training GANs. It was written by Tim Salomons and collaborators from OpenAI. And one of the authors in this paper is Pieter Chen, is one of the instructors, or he was one of the originators of this class too. So So basically, they propose a bunch of techniques like feature matching and mini-batch discrimination, historical averaging, virtual batch norm, and one-sided label smoothing. All these are techniques that we'll go into details, just like how we delve into the details of DCGAN. And we'll see what they are doing and why they're useful. So feature matching. Pieter mentioned that if you train the discriminator really to optimum, it's not very useful because you're not going to get sufficient gradients. But then if you don't train the discriminator to optimum, your discriminator is not good, and just purely focusing on optimizing this objective is not really great for the generator because you don't really have a good discriminator. So instead of just trying to make the generator optimize the output of the discriminator, the idea was, what if we looked at something else? So what if we took an intermediate feature, f, in the discriminator, and you passed your real data forward and collected the statistics, the hidden layer, from your intermediate feature layer of the discriminator. And you do the same thing for your generated samples. You sample a bunch of z's, you get your generated outputs, and then you pass the generated outputs to your intermediate layer of the discriminator. And you force the features of your generated samples to match the features of your real data. So this way, you're not just purely optimizing the output of your discriminator. You're also making sure that the generator produces samples that are consistent at various feature levels of the discriminator as far as matching the real data is concerned. And this is something like making sure that you hope that the discriminators learn some useful edge detectors and so on. And so you're just trying to make sure that these somewhat semi-low level statistics of the generated samples match the discriminator. And so the generator can't produce some garbage to cheat the discriminator anymore. The second technique is a very interesting technique called the mini-batch discrimination. So Pieter referred to some problem called the mode collapse problem in GAN training, where when you train a GAN, it's very likely that all this noise in your actual noise distribution is basically being mapped to a single point by the generator, and the discriminator is not really aware this is happening because it's just looking at each of these samples independently during multiple forward passes, and it's not aware of the diversity of the samples that are being produced by the generator, and it's just happy that it's able to confidently discriminate between the real and generated samples. So, yeah.
For the previous slide,
Yeah.
but it's not the same image that we want to match, right? We want the distribution over all the real images, all the images in the real time. How do you ensure that matches in general and not for each image?
Yeah, so that's why we're going to talk about the mini-batch discrimination. You mean to say, are we doing this for, are we ensuring that the statistics of the features match? We are, right? You're taking the first order, so this is the mean. It's a first order statistic.
Right, but just like it's a point estimate, right?
Yeah.
Why not match the distributions instead?
Yeah, you could. Like, you could try to match higher order or like even the standard deviation. It's just that it's more expensive. Like you would then calculate a covariance matrix, right? Yeah. Yeah.
So this seems similar to the Fréchet internal norm thing that was used to evaluate the performance of GANs earlier.
Mm-hmm.
And Professor Abbeel mentioned that directly optimizing that objective wasn't very useful. So I was wondering how this is different from that.
No, so that's a great question. So the question is, this looks very similar to the Fréchet inception distance, which is actually an evaluation metric for GANs. So this paper came out even before that, and they were not trying to design this objective with that in mind. And I'm not sure if anybody's actually tried to run this objective after that metric was proposed and see the correlation between optimizing for it and not as far as the evaluation goes. Okay.
In a way, it's a bit like a skip connection, isn't it? Just a way to enrich the signal going from the discriminator to the generator.
Yeah, you could think about it that way, though it's not actually a gradient flowing from that layer. The gradient is just going to flow normally. It's just that you have an additional loss. And so those weights which are trying to get you up all the way up to F, they're not going to get two gradients. One is from your normal discriminator output, and this is the extra loss.
But it doesn't enrich
Yeah, it doesn't change. It doesn't add new gradient paths, but it gives you more gradient for the parameters involved in getting you all the way up to F. So the second idea is in this paper is called the mini-batch discrimination idea, and basically the motivation here was that you want to make the discriminator aware that it needs to make sure that the generator produces a diverse set of samples and not just a few realistically looking samples. And just passing the generated samples in multiple independent mini-batches is not going to let the discriminator be aware of the kind of overall diversity being produced by the generator. So one way to ensure that is to incorporate some side information about what the other samples in the mini-batch being generated by the generator are. So what the authors propose is the following. Let's say your xi is one sample in your mini-batch, and it's producing a feature vector f of xi. So they use a tensor a times b times c. Let's say that this is an a-dimensional vector. And they use this tensor to project f of xi to a matrix mi, which has dimensions b times c, right? So now this matrix has b rows and c dimensions per row. And now you consider two separate samples, xi and xj in your mini-batch. And for a particular row b, so there are 0 to b minus 1 rows. And for a particular row b, you're just going to take the difference between the vectors in that row for these two samples. So you take the L1 norm, and you take the neg exponential of that. So this is a distance metric between the corresponding rows of the corresponding matrices of these two separate samples. And you do this for, you basically do this for every single sample in your mini-batch, right? So you have a mini-batch, and J is just one other sample. You can do, with respect to I, you can do this for every single sample in your mini-batch, and you add all those values, or add all those distances. And that gives you a metric of how differentiated the particular sample I is for the corresponding feature vector B, indexed as B in your matrix. And if you concatenate all these, this is just a single vector, and if you concatenate a single scalar, and if you just concatenate all these different scalars for different rows, you get a bunch of distance measures, right? So, and this is across your mini-batch. So you basically get a new vector, R b-dimensional vector for every single sample in your mini-batch. And then you can construct another feature, which is your mini-batch times this dimension. And what you basically end up doing is when you pass it to the next layer of the discriminator, you're passing f of x along with O of x. You concatenate f of x and O of x together, and then you pass it to the next layer. So this way, your discriminator is now aware of every single sample's distance to other samples in its own mini-batch, and so it's getting some kind of higher order across batch statistics as a feature vector added to your original feature vector. All right, so can we take a break now? Okay, let's resume. So among these 5 different techniques proposed for improving the GAN training, we've looked at feature matching, we've looked at mini-batch discrimination, and next we're going to look at historical averaging. So historical averaging is basically inspired from Nash equilibria, and so basically, the idea is to make sure that when you're having a complicated 2-player game, and there is always the issue of the saddle point optimization making things unstable, right? So, for instance, if you have a value function xy, and like say one of the 2 players is trying to maximize this with respect to x, and the other player is trying to minimize this with respect to y, then it is a good exercise to work out that like the game will basically be circling around in orbits around the center. So so basically that's one of the main reasons that GAN training is really a magic or like a black magic, and to figure out how to make it work. So the authors inspired from some techniques on Fréchet's gameplay in Nash equilibria, and try to have a penalty for the parameters in both the generator and the discriminator to be closer to their historical averages. And you can keep backups of your own parameters, historical averages. Like in general, it's basically the checkpointing system, right? So when you're running any neural network, you're always checkpointing your latest versions of the parameters. And there is a penalty for the parameters not to steer away too much from the previous versions. So this way, you ensure that the loss is not going to be too oscillating, and it's a good regularizer. Among these three techniques seen so far, these are like the three training techniques. Among these three techniques, the most useful, according to the authors, is the mini-batch discrimination, and the second most useful is the feature matching, and the third most useful is the historical averaging. Yeah.
Historical averaging seems like it could work for basically any model. Like, is it useful for neural nets outside of GANs?
Yeah, that's true. So her question was, it seems like historical averaging is a technique we should just use for any model you train. It's not specific to GANs. That's true, but in general, any model that you train is always using an exponential, is always keeping an exponential moving average of your parameters. And at inference time, you're always using the exponential moving average because that's better for validation or generalization. In GAN, it's very explicit, like at least in this paper, they found it important to use even during training time. Whereas in other cases, the loss is not too complicated enough that you need to ensure this kind of a stability. But these ideas, like for instance, making sure your parameters don't move away or making sure your output distributions don't move away too much, has also been used in reinforcement learning. For instance, in trust region policy optimization and general trust region methods, there is always a KL term that makes sure that the output distribution is not too far away from an older version of your policy. So different aspects, different instantiations of this high-level idea has been used in multiple places. Yeah. So the next trick that the authors propose is called one-sided label smoothing. But before that, label smoothing in general is like a very good idea to use, and it's been used in multiple places in supervised learning. So the key, basically the idea in label smoothing is the following. Whenever you implement a classifier, you're always giving it targets or labels, and you're saying the target is some one hot vector, right, over your like number of labels. So this is particularly like this is very clear. Like this, you just want the output to be one particular class, but in general, adding noise to this vector is useful because it's a good regularizer, and it's not really going to cost you anything. It's not going to reduce your accuracy too much. So let's say you change this to 0.9, and like let's say there are 4 other classes. You can just make the remaining ones as 0.1 by 4, 0.1 by 4, 0.1 by 4, and 0.1 by 4. So you're just adding extra noise, so they still marginalize to like 1, but you're just introducing this noise, and that way you make sure that the classifier doesn't have to be super confident. You can reduce the confidence, and that way the mistakes are made without too much confidence, and that's pretty good when training something like a GAN. And specific to GANs, it's very useful if you want to prevent like large gradients to your generator, because your generator gets gradients from the output of the discriminator. And so if your discriminator is not being so confident, it could stabilize the gradients that you receive for the generator. And but now there's a confusion, right? So you could basically do label smoothing for both the generator loss and the discriminator loss, because both have this output of the discriminator as a term that they're optimizing in different directions. So in the authors just propose to use label smoothing for the discriminator, and so they don't use the label smoothing in the other version for the generator loss. So the generated samples don't have any label smoothing, but the real data samples have the label smoothing. And the argument that the authors make is the following. If you write down the optimal discriminator for, given the label smoothing noise that you're adding, since it's a binary classifier, it's just not the way I wrote it. For instance, it's just going to be like 0.9 and 0.1, because it's just a binary classifier. If you write down this particular optimal discriminator, you end up with this term which is 1 minus alpha p data x plus beta p model x in the numerator. And alpha and beta are your noise probabilities for your real data and your generated data. So the authors make this argument that they don't want any p model term in the numerator because if the optimal discriminator is having a p model in its numerator, then it reinforces the generator to produce more of such samples. And so they remove the noise. They don't use any label smoothing for the generator output, for the generated samples, but they only use label smoothing for the real data samples. The argument or the reasoning is very heuristic. You should take it with a grain of salt. But this label smoothing technique is very useful for training GANs. So finally, we look at this thing called virtual batch normalization. So previously, I made the point that DCGAN uses batch norm for sampling at test time. And that's likely to produce correlated samples because you're basically sampling a bunch of Z's and like you're averaging over that in your generator, right? So sometimes it could produce samples like these where this is all looking really orange or this is all looking really green. And that's basically because of this intra-batch statistics dominating the generated quality. And so the authors in improved training of GANs propose to use a different version of batch normalization. It's called the virtual batch norm. And the way it works is as follows. First, we'll introduce something called the reference batch norm. So you can create a set of reference samples that are decided beforehand. Call them R1 to RM. And so for any minute batch X that you do a forward pass on, you have X1 to X. It could even be different sizes. So this is your mini batch. And your mean and the standard deviation are going to come from this reference batch. And you would use these mean and standard deviation when you do the batch norm. You do this, right? You basically do this, and you have this affine term. So this mu and sigma are going to come from R. But you would implement the same R for every single forward minute batch that you process. And this way, you're making sure that your batch statistics are not going to depend on your current batch at test time. So that's a useful trick. But there is a flaw with this trick. The flaw is that if you fix 1 minute batch for your whole training process, it means that your models could overfit to that particular minute batch you sample as a reference batch. So unless your reference batch is really, really huge, it's very likely that you're going to produce a very non-diverse set of samples. So, and having a very huge reference batch is not really optimal because you need to forward pass all these reference samples every time you do the updates, right? Because every single forward pass, you're going to calculate the, with respect to the current parameters, you're going to calculate what these reference samples are producing at every layer for your batch norm. So the authors introduce this idea called virtual batch norm, which is basically you take the reference batch norm, and for every single sample, you append your sample with the reference batch norm. So you're basically your statistics are going to be collected from that particular sample, as well as all the reference images in your reference set of samples, and you're just going to use all of them. So your statistics are going to be tuned for your current sample, and that way it's not going to be able to overfit to your reference batch, but it's still it's still pretty dependent on your reference batch. But it's probably the best fix you can come up with if you really want to use batch norm with reasonably small batch sizes. And remember that this was during times when like big batch training or large distributed deep learning wasn't really there yet, right? Like people were still training with single GPUs and at the maximum like 2 to 4 GPUs. So yeah, any questions on this so far? Okay. So one final aspect of this improved training of GANs paper is it introduced the idea of semi-supervised learning with generative models. Basically, the idea was that if your discriminator is going to take some image and predict real or fake, in addition, you could basically predict the category of the image and you could, and if your data set has labels as well, then while training your discriminator, every time you pass in a real data sample, you could also produce a classification loss for that real data sample, which means that when you do something like feature matching in the intermediate layer of your discriminator, then the feature matching is now going to be much better objective for the generator to optimize, right? Because that's like optimizing the feature layer of a classifier. And we know from experience in supervised learning that feature layers produced by classifiers are really semantic. And so trying to optimize the statistics of those semantics could produce better better quality in your generated samples. And it could also let your unconditional generator converge faster. And it could also let you do semi-supervised learning, which is you don't need to rely on having a lot of labels. You just need probably a few labels, and the discriminator is able to also learn representations from the unsupervised objective, as you've seen in DCGAN. And so it's a nice way to unify semi-supervised learning with generative modeling. And the authors have really good semi-supervised results on CFAR 10, which was considered really good at that time, but not that great anymore. But the fact that you could train a generative model as well as not rely on too many labels and produce really good samples was really cool. Yeah.
So I hear a lot of like evaluations being done on things like CFAR 10 or like these very restricted data sets. I'm wondering whether that's acceptable in this particular subfield, or if that's something you moved on from or now evaluating on ImageNet or richer data sets.
Yeah, so the question was, is CFAR 10 a good enough data set to focus on as far as metrics are concerned? Like I said, you should remember that the paper was not done at a time when a lot of compute was a common aspect of deep learning. So CFAR 10 is the best data set to work with if you're trying lots of these different variants, right? Because you want your results to come really fast. And it's still a good data set to try out your basic ideas. Like a lot of people still work with CFAR, even though it's a solve, it's the top one is close to 100% now and all that. It's still 50,000 images is still a good enough data set to like quickly see some signs of life or a new idea.
So when you're writing a paper in the field and like, you want to have like your minimum viable product, let's say, is there like a rule of thumb for that?
Yeah, so we could take this offline actually, because I mean, writing papers is like, there's a lot of other factors involved in it. Yeah. All right, so Inception Score was something Pieter already covered, so I'm going to skip over that. It correlates really well with human judgment, and it captures a lot of necessity for diversity, because you want to make sure that your generated samples are having as much diversity as your actual data set in terms of the class labels. And let's see. So these are the samples that were seen in the improved training of GANs paper. You could see that the CFAR samples are really good, but the ImageNet samples, they did an initial attempt, and they were like, you can see some dog-like images, but it's still not getting any, or it's like producing multiple heads of the dogs, or like, it's having a lot of these artifacts in the borders, and it's not really that good, but it was really good, considered good at the time. Cool. So next we cover the more modern versions of GANs after that, because these were all like a lot of nice tricks. So remember that Pieter focused on this aspect of GANs optimizing some kind of a distance metric between your real distribution and your generated distribution. And GANs are implicitly basically trying to optimize this Jensen-Shannon divergence between your real and generated. But you could also think of trying to design GAN architectures or models that are trying to optimize some other distance measure. And there is this distance measure called the Earth mover distance, which has inspirations or like foundations in optimal transport theory. Basically, the idea is, given a real distribution and a generated distribution, the Earth mover distance between them is basically this particular term. It looks complicated, but basically the idea is as following. Given a joint distribution between PR and PG, you can evaluate something called this, which is every expectation over samples coming from this joint distribution, the distance between those samples, right? So you could take x, y from the joint, and you could just evaluate the distance between x and y. And this could be any distance. You could define it with respect to any distance. So here they use the L2 norm. But and then if you take the expectation of this over this joint, and you calculate this for various joint distributions, and the infimum of over all those possible joint distributions is the Earth mover distance. It's clearly intractable, right? But we'll see how the war-sustained GAN authors have come up with a very nice way to like optimize this particular distance. So the way it works is they have this duality called the Kantorovich-Rubinstein duality that has a dual version of this objective, which is probably easier to work with. And the dual version goes as follows. It is the supremum over all one Lifshitz functions of this particular term, which is nicely decoupling the expectation. So you don't really have a joint anymore. You have an expectation over independent distributions, where this is an expectation over P real of f of x, and this is an expectation over, this can be defined with any PR and PG. I'm just using P real and generated so that you get the connection with the GAN. So expectation over x from PR of f of x, and expectation over PG of f of x, where there's like various different f's that are possible in the family of one Lifshitz functions, and you want to take the supremum of over all those f, and that's the dual version of this particular infimum term. It's still intractable, right? Because you're not going to be able to enumerate over all possible one Lifshitz functions. Firstly, like I hope like you're familiar with the definition of Lifshitz. It's basically that we'll go over the definition in the next slide, but this is the definition, which is basically that for an f that maps from x to y, f is k Lifshitz if you can have distance functions dx and dy on x and y, and make sure that dy in the map projected space, which is f of x1 and x2, is less than or equal to k times the dx of x1 and x2 for any pair of x1 and x2. So basically that you take a function, you have an input space, and any pair of points, you just map them to your output space. You want to ensure that the distance in the output space is only going to be only at most as big as k times the distance in your input space. So this is a way to guarantee that your derivative or your smoothness of your mapping is ensured, and it's a measure of how smooth your mapping is. So so that's basically the definition of Lifshitz. And the war-sustained GAN paper done by Martin Arjowski and collaborators is basically trying to figure out a way to optimize the duality of the Earth mover distance. And it's still intractable, but then they're going to come up with some few tricks to ensure it works. So the way it works is as follows. Basically, if it's okay for you to search over k Lifshitz functions, think about these functions being characterized by neural networks. And let's say there is a family, capital W, and you're trying to optimize this particular distance over that. And you can say for sure that if you have a particular family and you're calculating this particular measure, it's going to be less than or equal to the supremum. And this particular family is like family of all Lifshitz functions, so it's definitely going to be less than or equal to the supremum. And that supremum, if you have a Lifshitz constants of k, it's just going to be k times the Earth mover distance. So the key idea that they're trying to come up with is, even if this family is not as constrained to be Lifshitz functions, as long as it's somewhat approximately Lifshitz, you're optimizing some kind of a lower bound on your actual Earth mover distance that you're trying to maximize. So as long as you maximize, as long as you're trying to work with this particular loss, where you're basically having a max over some family that's approximately Lifshitz, it's guaranteed to be less than or equal to the supremum, which is the actual definition. So you can think about this as like the distribution that comes for PG could be characterized by a neural net, which is your generator, and then just optimizing this distance for the generator could let you work with the standard neural network packages and backprop. So after all this building up, I'm going to disappoint you with how they actually implement it. So if you look at the pseudocode of WGAN, and I've built up all the Lipschitzness math and all that, but at the end of the day, all they do is this is the Lipschitz regularization. So they just clip the weights. They do nothing else. It's just basically clipping the weights to lie within a particular value, and they do the regular GAN objective. But the most important thing I want to highlight is they move away from this binary classifier version of GANs. So they have the discriminator, and the discriminator is just a neural network that's something like this. It's just FW, which is taking in a real data, or it could take in a generated data, and it's just outputting a scalar value. And you just ensure that this FW is approximately Lipschitz by clipping W. So there's no classifier now. So they introduced this notion called a critique, which is familiar to people who work in deep RL, which is basically, you can think about the generator is trying to maximize the value of the critique, while the discriminator is trying to minimize the values for the generated samples and maximize it for the real samples. So that's a clear departure from the original way in which people thought GANs. People thought about GANs was, oh, the generator is a classifier and the discriminator is a classifier between the real and fake samples. But the way they implement the Lipschitzness is very, very trivially, like weight clipping, and that's not the best or the most principled way to do it. But they do have amazing results, which was pretty surprising to everyone at the time. So one thing about a classifier, which Pieter talked about as the saturating problem, which is that if you have a classifier, and this is like, I guess the blue is real, and this is fake, or the generated, and these are the distributions. It's all 1D. Now this is the discriminator, and it's clearly classifying the real from the fake. But the gradient for the fake samples or the generated samples of the discriminator is 0. So it's the generated samples are not going to get any gradient from this kind of a discriminator. But look at this Wasserstein critique, the blue line, this one. It's clearly giving you a constant gradient because it's close to a straight line. So the slope is non-zero. So the generated samples can actually get gradients, whereas the previous version of GAN has that is the saturating version, has vanishing gradients. This is a bit controversial, right? Because if you compare it to the normal GAN, nobody uses the normal GAN in the original loss. They use the non-saturating version, which is where the generator just maximizes the log probability of the generated samples rather than trying to just exactly optimize for the negative of the discriminator loss. But so that's, you should take this with a little caveat, but in general, this is a cool fact that you can get a critique to work this way. So they show that the Wasserstein estimate, the Wasserstein distance, is pretty correlated with the sample quality, and over training iterations, as the generator keeps training, the Wasserstein distance keeps going down and the samples keep getting more and more real. And this is with the DCGAN architecture. Whereas for the Jensen-Shannon divergence, they have their own way to estimate it, and it's not particularly correlating with the sample quality. The main thing that they wanted to show was with exactly the same architecture, just by changing the objective and the training mechanism, the the WGAN samples are on par with DCGAN. And that was really cool. So it's like a new GAN family, but it's working as well. But not just that, they showed that WGAN is somewhat robust to the architecture choices compared to a DCGAN. You saw that DCGAN involved a lot of hacks, and I really stressed that DCGAN wouldn't really work without batch norm, and you can see what happens. Whereas a WGAN seems to be pretty decent, and it could still work without a batch norm. And they also showed that WGAN can work with MLPs better than a normal GAN with the same architecture. So the summary of WGAN is that in my opinion, this is the most useful summary, is that you're basically moving away from this the saturated binary classifier version of GANs to something like a critique. where D is a critique, and your generator is just optimizing this particular objective. And this max over Lipschitz families is basically implemented with weight clipping. So again, the authors themselves say that it's terrible, and if because there are reasons, like if the clipping parameter is large, then it can take really long time for the weights because there's a lot of values they can take. And if it's really small, you're going to get what you usually know as vanishing gradient, because the gradients are all scaled by activations, and if your weights are low, your activations are low, and therefore your gradients are low. So, but they encourage people to work on it, make new versions of Lipschitzness, which was really, really useful. And the next version was called the WGAN GP, which is basically improved training of Wasserstein GANs by Ishan Gulrajani and others. So it's basically going to change the wave clipping version. Yeah.
So before we used gradients, we had like sigmoids, right? So this is like having sigmoid as your non-linearity would have like enforced Lipschitzness in a way if you also have like different wave matrices that like ginormous.
So your Lipschitzness is basically, you can think of the discriminator as your whole neural net in your discriminator, right? That's the function it's actually representing. So just changing the output won't ensure that it's Lipschitz. Because I know that what your argument is that sigmoid is a bounded function, and so its derivatives are like you can actually define a Lipschitz constant for that. But the the computations so far till then, they don't need to obey any kind of Lipschitzness criterion, right? So unless you make sure that at every layer, every single weight is capturing some aspect of Lipschitzness, you can't guarantee that. Because it's a composition of functions, right?
Yeah, okay. But if you had like sigmoid non-linearities throughout, and like neural networks are generally relatively smooth, like
Mm-hmm.
you sort of get pretty like a pretty Lipschitz function, because like it can't jump too high.
Yeah.
Between every layer, right?
Yeah. So that's generally true, but in GAN training, it's pretty because of this adversarial training, your training dynamics are not going to be the same way as regular, like say likelihood-based models, because you're basically trying to do saddle point optimization here. You're not trying to calculate some global or local minimum of like a regular function.
Aravind, I propose we take all remaining questions after lecture.
Okay.
There's a lot to cover, and questions take up a lot of time.
Okay, sounds good. Cool. So the improved training of Wasserstein GANs has a new way to ensure Lipschitzness through this idea called a gradient penalty. I encourage you to look at the actual proofs of these propositions and corollaries. They're pretty involved, and it's in the appendix of the paper. But the key idea is as follows. This is the Wasserstein objective that you already saw. And the way they enforced Lipschitzness was just using weight clipping. In this paper, the addition is they add another term for the gradient penalty of the discriminator with respect to its input. So what is Lipschitz? You're trying to make sure that the derivative with respect to your input of your function is not going to be too big, right? So if that's what you care about, if it's all about the magnitude of the gradients, then if you have a discriminator and you feed in a particular input, and it's going to feed in an output, right, for the next layer. So you can take the gradient with respect to the input of your discriminator. So this particular term is grad d of x hat with respect to x hat. So it's going to be the same dimension as your image dimension. It's a pretty large tensor. And you're going to take the norm of that and try to make sure that it's close to 1. Why 1? You should check out the paper, though people have also tried trying to not use 1 and just trying to just minimize the norm. Basically you have a lambda term that figures out how much you want to give importance to this. And the final thing is this thing. So what are the samples over which this loss is average? Is it the generated samples? Like to the discriminator, you're feeding in generated samples as well as the real samples. So you could take the gradient with respect to the input for both of them. But the authors figured out that if you take a mixture which is you take a particular generated sample and you pick a particular real data sample and you do a convex combination of them. And this is your sampling distribution just for the gradient penalty objective. It's heuristic. It's not really principled or well-motivated, but it is the version that works the best. You could think about it as smoothing the manifold over which the Lipschitzness is enforced, and therefore making the training work much better. So the pseudocode is not going to change much from the WGAN, except for this term, and no weight clipping now. Any questions on that? So they also use atom instead of Armis prop. That's another change from WGAN. And the final point I want to make with WGAN GP, which became a standard in all the GANs later, is no batch num in your critique or your discriminator. So the reason they went for it is not like, oh, let me see if I can get rid of batch num in the discriminator. It's more because their objective, which is using a mix of your generated and discriminated samples for your sampling distribution for the penalty term. Therefore, implementing separate batch num statistics for generated samples and discriminated samples was not optimal for them, because a lot of the objective is looking at a mixture distribution now. So they just got rid of the batch num because they didn't want to figure out a new batch num for the combined statistics. And because that architecture worked really well, this became a standard in every single GAN after that. Nobody uses batch num in the discriminator anymore. So WGAN GP was more robust to the architecture choices. So they did a lot of ablations. So they tried various nonlinearities in the generator discriminator, different depths, whether there's a batch num or not, and layer num for the discriminator, and also number of filters and so on. And it turns out that WGAN GP succeeds on a lot of architectures compared to like regular GANs, and so that was a cool result. The robustness is a lot more now. And you can also see it visually about how WGAN GP produces better samples than WGAN clipping, which is the original WGAN, across various different versions of the architecture. And finally, the bedrooms got better. So that's what matters. Yeah. All right. So it was a state of the art on CFAR as well, on Inception Score. And it's a very highly adopted architecture or model. Like a lot of people just take that code and just run it on a new data set, and almost always works. So the paper is very highly cited. So this is a summary. These are really cool, but there are two negatives. First negative is the wall clock time is going to be much slower now for training, because your gradient penalty term is in your objective. So just to construct your loss, you need to do another backward pass, right? So that's like one extra backward pass and then a backward pass after that. So it's much slower than just training a normal GAN without the gradient penalty, right? So, and the second thing is the heuristic distribution of your gradient penalty could be unstable, because it could focus too much on your current generated sample distribution. And so your atom is generally run on WGAN GP with a very small step size. So if you really want results very quickly, WGAN GP is not the model that you want to use, because it needs to train much slowly, much more slowly, and like with a much smaller step size. So the next model we're going to look at is progressive growing of GANs, or ProGAN as it's called. This is a paper from NVIDIA, and this is a cool paper that shows what happens if graphics people come and take over GANs. So this was the first high quality samples ever produced in any generative model. And you can look at the samples, right? These are the samples, and they're generated samples. So like not even any you saw bedroom so far, but like this quality of faces is much better. And the key idea here is to progressively grow the size of your images, both for the generator and the discriminator. So you start with 4x4 images, very, very downsample, like, these pixel art style, very minimal 2-bit kind of models. And then you're basically upsampling the spatial resolution by a factor of 2 every time. And you're reusing the layers that you already trained and just for adding the next downsampling or upsampling layer in your generator and the discriminator. And it doesn't generate just faces. It can also generate like various categories in the LSEN dataset. So very realistic. Like can generate like Android phones and all that. It's pretty cool. Cycles, animals, everything, real world objects. And the bedrooms got better. So yeah. These are also 1 megapixel images, which is unheard of in any generative model till then. And this is, you can see how it's it's able to slowly scale the size up across various layers. The exact details of the architectures, it's not in the scope of the lecture to go into it. You're really encouraged to go and read the code because the paper is hard to read. So the final version, or the final set of versions we'll talk about is the GAN and its follow-ups, which adopted it. This was a very important paper, and this is a lot more principled than just upsampling, downsampling, and it also produced amazing samples. So for that, we need to understand like fundamentally like a few ideas on Lipschitzness. And as somebody asked before about how what if you just put a sigmoid at the end? Wouldn't it be Lipschitz and all that? So let's try to go over that. Now imagine this is some deep neural network, and these are all like weights that are multiplying, and this is the activation. So the activation could be something like a ReLU. And you could think of your discriminator as some neural net that takes a stack of affine transforms and puts nonlinearities, right? And this is your GAN objective, like your usual, expectation over log dx, real plus log 1 minus d x prime generated. So you could think of that as your objective, right? And now, instead of maximizing over d, you could just in the WGAN style, you can think of maximizing over K-Lipschitz functions of this particular objective. So that is really the WGAN story so far. Now, this paper talks about how to enforce Lipschitzness without weight clipping or gradient penalty in a more principled way. So for that, let's focus at every single layer, what happens. So G is a layer that takes in H in and outputs H out. These are hidden layers. And you could define the Lipschitz constant of a particular linear transform as this particular term, which is the spectral, this is the spectral norm. And this is your gradient with respect to your input. This gradient with respect to your input. And G is some layer which takes in H in, puts a weight matrix and a nonlinearity, and outputs H out. So firstly, what is the spectral norm? For those of you who are already familiar with optimization or linear algebra, spectral norm is this written this way. It's this particular optimization problem, which can in turn be written this way, which is max over all vectors bounded by unit norm of A times H. That's the spectral norm for this matrix A. And this is basically the largest singular value of A. If you do a singular value decomposition of A, this is the largest singular value. You can read up on why it is the case. So given a particular linear layer with a ReLU nonlinearity, if you take an input H and multiply by W, the gradient with respect to H is just the weight matrix, right? So this particular term is basically just going to be the largest singular value of your weight matrix. And we will use another inequality from Lipschitzness, which is that if you compose two different functions and take the Lipschitzness of the composed function, the constant is going to be less than or equal to the product of the individual functions. So now with all these tools, let's just take the layer and do the forward passes and figure out what the final Lipschitz function of your discriminator output should be. because you can think of a neural net as composing functions on top. So you just upper bound the Lipschitzness of the whole function as the product of the individual layers' Lipschitzness. And every single nonlinearity's Lipschitzness is just 1 if you use ReLU nonlinearity, because the slope of ReLU is 1. So that way, your Lipschitzness of your entire discriminator ends up becoming the product of the singular values of every single weight matrix in the discriminator. And the idea in spectral norm is to take every single weight matrix and scale it by singular value, or the spectral norm. So that's why it's called spectral normalization. You take the weight matrix, you calculate the singular value, largest singular value, and you just divide the weight matrix by that value. And you do this for every single weight matrix. That's literally spectral norm. And if you do this and you train it with this, you're basically ensuring that the output is very Lipschitz. So far so good, right? One obvious question is calculating the largest singular value tractable for kind of the dimensions that we operate with neural networks? So that's where they were very clever. And so before actually I get into the details of how they do it, I also want to point out one more key change in the GAN loss that they did, which was to adopt something called the hinge loss, where the loss for the discriminator became something like an SVM classifier, and for the loss for the generator just remained the same. And it turns out this version works better if you care about optimizing the Fréchet inception distance. Somebody asked previously, like, how do you try to optimize directly for that, or like some devise objectives for that? It turns out like this is very correlated. Optimizing for the hinge loss is better if you care about the evaluation metrics more. So here's the architecture of SNGAN. I'll still tell you how they implemented the spec norm very efficiently. But the architecture is very, very similar to the WGAN GP architecture. It uses downsampling for the discriminator and upsampling for the generator. And the labels, if you work with labels, your labels are just concatenated at some point in between in your discriminator. And in your generator, they're used in something called the conditional batch normalization, which we'll look at in the next slides. So this time you're seeing like even pizzas, right? You just had pizzas. So GANs can generate pizzas. They can generate a lot of good-looking dogs. So I think it's just GANs are we're just getting better and better, and this paper improved it even further. So let's now look at the conditional batch norm idea, how spectral normalization is implemented at every layer, and finally just like let's just summarize everything the SNGAN paper then. So before looking at conditional batch norm, I want a lot of people who are not aware of how batch norm works for con layers to be aware of it. Batch norm means you're averaging statistics across your batch, but in a convolutional layer, your effective batch size is multiplied by your spatial resolution. You're taking your average across both your batch dimension, your height dimension, and your width dimension. So this is really like the standard con batch norm that everybody uses. And these are like your gamma and beta are just some learned variables. So this is batch norm. Now, what happens in conditional batch norm is this particular term, where the gamma and beta are functions of your, are some functions of your class variable. So your gamma is some function of your y, and your beta is another function of your y. And these gammas and betas are what is used to do the affine transform of your normalized input. So this way, you're fusing in information of your class variable at every single batch norm layer that's there in your generator. And therefore, this is much better than just feeding your class variable right in the beginning and not doing anything about it at all. This way, your generator is like really aware of what class it's trying to generate, and it's averaging the statistics at every layer to make sure it produces an image of that class. Now with spectral normalization, this particular variable that takes in the class variable and tries to produce the gamma and beta, or this particular weight matrix that does that is normed by its spectral norm. So that way, even conditional batch norm variables are using spectral norm. So here's the spectral norm idea. It basically is like if you've done power iteration before, you're very much aware of it. But it's really the simplest version, which is you take a weight, you take a particular pair of vectors u and v, and you just take your matrix that you're trying to calculate the largest singular value for, and you just try to multiply it with w times u and normalize it, and you can initialize that as your next v tilde, and then you take v tilde, it'll be a transpose because your matrix is rectangular, and you multiply that with v tilde, and you figure out what is the next u tilde. So for a square matrix, it's basically just saying that if you just keep figuring out, you take a matrix A and you just keep calculating A times V multiple times with the latest V, you converge to a fixed point, and that's your singular vector. So for a rectangular matrix, you need two different vectors of the row and column dimensions respectively. And the most important thing is you're going to backprop through all this, right? So because you're going to backprop through all this, you're not going to get gradients for V and U. So you put a stop gradient on U and V and U. And you're only going to take gradients for your weight matrix W. And you take the normed value, and you're passing it to the next layer. And you do all the operations with it. So this is basically how spectral norm is done. Now here's the magic. This is the magic. You just need to do one iteration of that. You would imagine that converging to the fixed point is going to take you a lot of time, and therefore is super infeasible. But the magic is you just do it one time. So it's just one single forward. In a single forward pass, you can calculate it super efficiently, and you don't even need to do the explicit spectral norm so correctly, and it still works. Everything works. So that's literally it. This is now the final detail is spectral normalization is very obvious if you use a dense layer, because you just take the matrix and you multiply it, and all the math works out. Now for a convolutional layer, your weight matrix is not exactly a matrix. Your output is not exactly a matrix multiplication of your kernel with your input, right? It's repeatedly applied at multiple layers. But it turns out that if you just take your weight kernel tensor and you just flatten it, and you do the same thing that you do for a dense layer, it still works. In reality, a convolution is actually if you want to write a convolution as a dense layer, it has the structure like a Toeplitz matrix. And so that's where you need to apply spectral normalization on. But in practice, the authors just got it to work by just flattening the kernel and getting it to work. That's kind of, I thought that was pretty amazing. So this is the summary of SNGAN. It produced high-quality class-conditional samples at ImageNet scale, and the first GAN model to work on full ImageNet. And it has a lot of computational benefits over WGAN GP, and uses way more principal versions of ensuring Lipschitzness. So you can see the computational benefits are very clear, right? So WGAN GP is really slow. This is like a forward pass over 100 Z vectors. And you can clearly see that SNGAN is like pretty much more stable and comparable to weight norm in terms of the inference speed. So SNGAN also used this idea called the projection discriminator, which also came from the same set of authors from preferred networks, where the class variable can be inner producted with the intermediate feature layer of your generator, and then so this is how you want to apply the class variables or feed in the class information for your discriminator. And so the version that I showed you just concatenated it somewhere in between. But you could also imagine introducing more multiplicative interactions by taking inner products and then concatenating the inner product at the end. So that version also works. It seems to work much better. So SNGAN worked, and authors from so Han Zhang and other people, Han Zhang, Ian Goodfellow, and others, they took SNGAN and introduced this self-attention architecture on top. And we know from previous classes that self-attention is really useful. So basically that's what they did. You take a convolutional feature map, and these are your query key value. And you basically do Q times K transpose, softmax. This is your logits. And then another matrix multiplication, output projection, and self-attention. That's it. So they have a scalar instead of a actual output projection, which is somewhat different from regular self-attention. But otherwise, it's pretty much the same. And sorry. So one other difference is it applies spectral norm to both the generator and the discriminator, whereas the SN-GAN theory was that you just wanted to make the discriminator Lipschitz, and you don't really care about doing it for the generator. But it turned out that it was good to use it in the generator as well. So it's a good regularizer. And it uses self-attention in both the generator and the discriminator, adopts the hinge loss that we saw. And it actually was able to produce very good samples even without class labels, which was not the case for SN-GAN. And it adopted the same mechanism for the class conditional version. So you can really see the samples are getting much better, much more diverse, and it was able to work at ImageNet scale. And the Inception Score increased a lot, like a significant increase. And the Fréchet inception distance significantly reduced. So it was really surprising when it came out. So now with all these tools, you know that. So what is left over, right? I think the leftover part is just to scale everything. And that's what happened in Big GAN. So these are the samples. It's not even comparable to what you saw so far, right? Like it's basically as good as a real version, unless you magnify it and look at what's going wrong at the pixel level. So this was basically ImageNet 512 by 512 class conditional, and it was able to interpolate really, really well between very different images. And so one thing that the authors recommended in the Big GAN paper is this trick called the orthogonal regularization, which is complementary but not the same as doing spec norm. Is you take your weight matrix and you try to make it orthogonal. And to make it orthogonal, you just need to take the transpose and make sure it's identity. And this was something done earlier. And in Big GAN, what changed is in your identity matrix, you don't want to penalize the diagonal terms. You just want to penalize the non-diagonal terms. And they show that version works better. So that was the change, only change, mathematical change in Big GAN. And architectures-wise, they have two different architectures, Big GAN and Big GAN Deep. When first Big GAN came out, they were not able to make it work on deep architectures. So they had to feed in the class information by splitting the Z vector into different parts and feed it at different levels. But then they figured out how to train it with a deeper model, and they got everything working. So this is not really relevant now. But the deeper model just feeds in the Z and the class at the beginning, and the concatenated vector, the same vector is fed at multiple levels for the conditional batch norms. So this is the architecture of Big GAN. Like it adopts a very similar mechanism to the WGAN models. There are like residual blocks, and it could be either upsample or downsample, depending on whether you're using the discriminator or the generator. And this is the Big GAN Deep architecture, which is the residual blocks here are more similar to what you use in a classifier. And the main trick is whenever you do downsampling or upsampling, if you're trying to go in your channel upsampling, if you're trying to go from C to 2 times C, which is you're just going to double the number of channels, what they do is they don't do 1-by-1 cons that takes in a dimension D and multiplies it to 2D. They just retain half the channels. They just retain the channels they have and just try to predict what they need to add. And whenever they need to drop it, they just drop it. They don't do a 1-by-1 con. It seems to work much better as far as metrics goes. So that's some trick that they discovered in Big GAN. So basically, Big GAN, these are the salient bits. Increase your batch size as much as possible. So if you have a lot of TPUs, you can, like I think they use 512 cores. which is basically like fire until voltage, right? And use cross-replica batch norm. Your batch norm statistics are not just averaged over your mini-batch in your current device, but in your local device, but it's averaged over all the different cores. And you increase your model size, you make it wider, you make it deeper. You fuse class information at various levels using conditional batch norm and projection discriminator, use a hinge loss, and use something called the orthogonal regularization and the truncation trick, and you can get amazing samples. So you can look at the ablations in the paper to see like how much each of it helps. They've really ablated it well. And all the inception scores and Fréchet inception distance are way better than the GAN metrics that you saw. And they also use the self-attention in the architectures. So one main trick is that they use something called the truncation trick, which is you sample Z from a normal distribution, but you truncate the values. You clip the Z that you sample so that it's within some constant range. And they found that this orthogonal regularization was so useful to allow them to use this clip sampling, because the sampling distribution at test time is changing from the sampling distribution that you train with, because at training time you don't clip it. You only clip it for producing like more realistic samples, and you don't want to produce like spurious samples. And they found some of the regularizations to be pretty useful to do this at test time. And finally, they make sure that at sampling time, unlike DCGAN, which relied on batch sampling, they actually ran various forward passes of different noise vectors at test time, collected a lot of statistics, and used those statistics to sample for any single image now. So that way it could work even with this. If you just want to sample a single Z, you just take a single Z and pass it forward. You could use a lot of these test time statistics for the model. And while it could produce a lot of cool images like a house, a bird, it could also produce some mixture of classes here. So this is a dog and a ball. So it became a dog ball. And let's see. And like you saw, the interpolations are really cool. You could play around on the TensorFlow hub of the release models. So finally, we look at style GAN. It is the latest and greatest of GANs, basically. So style GAN is an idea that they moved away from this concept of introducing a Z right at the beginning. You already saw that in Big GAN, they tried this idea of splitting Z into multiple parts and feeding it at different levels. Style GAN took it to another level where they basically said, there is no Z you feed in at all. You just take the Z and you have an MLP that maps Z to another W. And all you want to do is take the W, adapt it in terms of what you feed in at various levels, but don't feed anything directly. You just start with a constant vector. So this is a constant learned vector. And there's no stochasticity here. The only stochasticity comes from feeding W's at different levels. And you could think of these as style vectors. So these style vectors are based on what they do at every level. They're functioning as style variables of different nature. At a more higher resolution, they are behaving as more fine-grained styles. At a more lower coarse resolution, they're behaving as more high-level aspects like pose and all that. And I'll show you some examples. And finally, there's this noise variable, which is the Gaussian noise. It's very common in GAN training to add both input and feature noise at various levels. And so they also add a Gaussian noise at various levels. So a crucial trick in style transfer, not specific to GANs, it's a style transfer trick, is called instance normalization. In instance normalization, if you have a tensor batch height with channel, you only take the average statistics over your spatial dimensions. So you calculate separate statistics for every single sample, for every single feature map. And that's very useful in style transfer. You can actually look at this paper that proposed instance norm for style transfer. So the style GAN authors took instance norm and made sure that these affine transforms on top of that, just like how you saw in previous GAN architectures. Now these are a function of your W vector that's coming in at various levels. So this is some f of w, and this is some g of w. And this is done for every level. So this is called the adaptive instance normalization mechanism in style GAN. So this is the style GAN transfer. Now this is a source A, and this is source B. And this is more like middle, and this is coarse. This is fine. So you can see that when it's doing the middle, when it's doing the coarse things, it's retaining all the backgrounds from source A and taking the other aspects from source B. Whereas when it goes more middle and fine-grained in source A, it's retaining more fine-grained aspects like the eyes and the nose structure, everything. And, but it's taking things like the hairstyle and the background from source B. So it's basically figuring out a bunch of latent variables, which are like rendering variables. Some of it is going to be like high level, like the background, the lighting, the hairstyle, like the hair color and all that. And the low level details are like the eyes, the nose, the way the face is structured and so on, whether there are glasses or not, and whether they have like facial hair, everything. And it's going to combine and mishmash these two things based on like what is the particular style vector that you're modifying, which source you're taking which vector from. And this is basically the dream, right? In a generative model, you should have these hierarchy of features, which lets you learn very different things. Some of them are very fine-grained, some of them are more semantic, and style GAN lets you do that in a completely unsupervised way. And these are like really, really realistic-looking faces, right? Like, unless you really focus on the details, it's really hard to say these are not generated from a GAN. And the effect of adding the Gaussian noise at various levels is also clear. The left is basically without Gaussian noise, and the right is with Gaussian noise. And you can see that the left is more like, if a painter were to paint the same person, it doesn't have the rich detail of the skin, as the right has, like it has more low-level, fine-grained lighting details and so on. So that's it really for today's lecture. Like, you've seen a lot of GANs. You've seen how GANs have progressed from very foundational math that Pieter did to like very architectural details that I covered. So if you're like looking to do something new in GANs, both are really important. That's the message. You can't do one without the other. Thank you.